So hello and welcome to the computer graphics practice video, and this week we'll be moving on to shading and lighting. So very interesting topics, and in this task, so the first task is this shaded chopper, not shader chopper, so shaded chopper, and in this task we'll be implementing the Fong's lighting model, but with corrode and foam shading. So the difference here is, as you can read from the material, that with corrode shading we'll be calculating the color value at vertices and interpolating along the face. With foam shading we'll be calculating the color values or doing the lighting calculations at each fragment. So corrode shading is historically, it was before foam shading, because at those times there wasn't enough resources, or the GPUs weren't powerful enough to calculate the entire lighting calculations at each fragment. So they did it at each vertex. So let's open up the JavaScript file. So let's look at the code before we actually get to the shading. So we have a couple of shaders here, and what we'll be doing is at the key press we'll switch between the corrode vertex and fragment shaders to Fong vertex and fragment shaders. So those two variables will hold the shader codes that we are currently using, and those allow us to switch between different shaders. So a couple of variables here. The status container, this is an HTML element that shows, you can just display that, like put text in it and show which code is currently run. Now we have a light source, and we have a point light that moves around in the scene, and there is this light trajectory. This light trajectory is this Catmull-Ram curve, cubic curve, so or even like a spline, and this is just kind of a defined path. So we'll be looking at curves and splines in Basic 2 later on in the course, but currently it's just this path that kind of goes around in the scene. It's a curved path, and this trajectory allows us to sample different location points along the curve. So we'll use this here to get a point at some certain time and use that as the light position. So this is the coordinate where our point light source currently is. Right, so here you can see that, well, this is the same as before, but here we take different shader codes. This is the status element, camera is the same. This change shader changes the shader, and here we set the initial one. Right, and at arrow keys we call the change shader again. This does nothing fancy, it just loops in this 0-1 cycle, and if it's 0 we assign the corrode shader, if it's 1 we assign the Fong shader, and that's about that. Of course, like when we change the shader we have to change it for all of the objects. So currently we go through the entire scene, find out if an object has a material and it's a shader material, then we change the code. Now this isn't like the most optimal way of doing things. It would be better to put like all of our specific objects that we want to change the shaders for in some array, and then loop through that, because we'll be not only doing it here, but we also need to do it each frame to update some uniform values. So it would be more practical to put those objects in an array, but for like simplicity of the code, I wrote this traverse function. Okay, now in the draw loop we sample the light position from the curve, and now here we need to update the light position. So this light position is required for all of the shaders, and if it's changed, then we need to update it for all of the objects. So here you can read the comments. Send the light position transform to camera space. So this line is actually given like for you, so it's uncommented. And what we're doing here is we are taking the light position and we're applying the camera matrix world inverse to it. So this moves our light position. That's like this curve we have here. This is in world space. Of course, it could also be in camera space. But it's then it would move with the camera if the camera would move. But currently it's in world space, and we use this matrix world inverse. This is the view matrix. We use that to move this light position to the camera space before we send it to the shaders. And this is because we want all of our variables, all of the coordinates, vectors, and so on to be in one space. It doesn't matter if they are all in world space or all in, I don't know, objects local space, although that would be, you would need lots of computations to like move, well, it's not lots of computation, but you need to move each light to the object's local space. Yes, you would need an inverse of the model matrix and that. But usually people prefer the camera space for doing the lighting computations. So here as well, we move everything to the camera space. Hopefully you have rotated your plates with something like this, although if you have like this children one might not also be the best idea here. I think there's also this method that allows you to fetch the children by name, and then you can have your children with name attributes, and that would be much better, because if the hierarchical structure changes but the names stay the same, then this code would still work. But yeah, for simplicity it's that here. So here we have your regular add hanger and chopper and stuff functions. You can see that we now have a sphere, so our chopper will be a sphere, so that the body at least, so that we can see what happens with the shading on this curved surface. And this great shader material, well, here we need to send or define two uniforms. We need to define the light position and, well, the color of the current material. So to define uniforms, it's we say the name, light position, and next we need to specify the type. And for the light position, the type will be a vector 3. And well, value, because we'll be updating it, well, we could put light position here, but it doesn't really matter because we'll be updating it each frame. But as for the color, the type will be C, so 3JS knows that this is this color object and how to take the RGB values from it. And we put the color here because this color, as you can see, it's this color code from the color object sent to this function. Okay, now we have those uniforms defined, and we reach those shader codes. So what we'll be doing is we'll be trying to implement the Phong lighting model or reflection model in this corrode vertex and corrode fragment shaders. And corrode fragment shader will be very simple. We'll be just interpolating the color, and this will be the output. But here we do need to think about the actual lighting model. So let's see if we can remember how, from the lecture, how Funks lighting model was. So we had some kind of material ambient term, light ambient term, then we added material diffuse term times light diffuse term, and this is the part where we needed to know how much of our light actually shines on our unit surface. So if we have some surface, the question was, is our actually, let's draw it like this. If we have this unit of light, so how wide the surface it covers. So if you have the same unit of light this way, it covers a much larger surface than if it were perpendicular to the surface. And we found out in the lecture that how to calculate this is that we need the surface normal and the direction towards the light source. Now those of course need to be normalized, and we take the dot product. The cosine of the angle between those two gives us the correct value that we need. So we take the normal and the direction towards light. Now if this is negative, then we need to clamp this. And lastly, we have the material specular and light specular, and for the Funks lighting model, what we need here is the direction towards the viewer and the reflected light direction, and this thing is raised to the power of shininess. Shine is good. Okay, so if our light is coming here, this is our surface normal, then we need the R, the reflected light vector, and if our viewer happens to be here, then we need like the viewer vector and the cosine of the angle between those two vectors raised to the power of shininess gives us this exponent here, of this term here in the specular term of the Funks lighting model. Okay, so what we did discuss is that we actually, when we were implementing this in this task, we don't need some of those things. For example, we can define this thing as some single small value, some vec. Actually, not the ambient thing we still need. So usually the material ambient and material diffuse is the same. So if this is the same, then what we can do is we can bring the material property out of this, and we have some small value for the ambient light plus this diffuse light intensity times the normal times the light, the vector towards light. Right, for the specular term, what we can do is usually we can say that well, this will be this will have the same color as the light because the light will not emit a different color usually in the specular term. As for the material specular term, this will usually be white. So what we can do here is that we can just add this term. So in the task we can also assume that light intensity is white, perhaps. So this term actually will just be vector times the viewer, the vector towards the viewer times the reflected light vector raised to the shininess power. So let's see how this would look like in code. So the things we need. So we need the normal, the vector towards the light source, vector towards the viewer and the reflected light vector. For those things, like we want them all in camera space. So in that sense, we need to find out where is our fragment in the camera space. So for example, like if we're trying to find out this vector towards the light source, then the light position, if we have the light somewhere here, this we already transformed into camera space. So this is already represented in the camera's coordinate system. But this position of our current vertex is in the local space. So if you look at the code, remember we have this position value that Three.js sends automatically. So first we would need to calculate the vertex position in the camera space because the current position is in local space. So first step, let's create a new vector tree that will be a vertex position, for example, and that will equal to. And now how to transform your vertex position into camera space. So to transform it from the local space to world space, you would need the model matrix, and from the world space to camera space, you would need the view matrix. But as we know, we have a model view matrix, so we multiply this with the position, but the position we need to move to homogeneous coordinates for the translation to work. So position 1.0. And because we want this to be a vector tree, and there isn't like any perspective projection that would change this ladder 1 here, then what we can do is we can take the x, y, z components of this, the result of this computation. So now we should have the vertex position. Next, we need to calculate the correct normal. So in the diffuse term, there is the surface normal, and we do have the surface normal. So let's see, there's probably some kind of an error here. If okay, we have a colored object. So, okay, let's make an error to this code. And if I refresh this, we can see that Three.js sends us a normal. So vector 3 normal. And that is in the object's local space. And we need to move this to camera space as well. Now, in order to do that, your model view matrix doesn't do the trick because if you have some scaling in there, then your normals may be wrong. For more information about this, I recommend you to read this article. So this shows you that if you try to use the model view matrix on your normal with 0 as the last value in the homogeneous coordinate system, then the result isn't perpendicular to the surface. And there are other problems, and there is the derivation for the normal matrix, and it happens to be the inverse transpose of the model view matrix. But we don't need to calculate this. If we look at the code, then Three.js does send us the normal matrix again by itself. So what we want is a normal, so let's call it n, because we'll be writing a big formula using this normal later on, and this will be normal matrix times the normal. Now if you do that, then your normal might not be normalized. This normal matrix will keep it perpendicular, but it might change its size, so we normalize our normal here. Okay. Always make sure that the vectors you will use in the dot product to find the cosine will be normalized. Otherwise, like, you might get some visual artifacts, and they might be even hard to see in some cases, but then be apparent in others, and then you don't know what's wrong. Next, we want to find the direction towards the viewer. So this will be towards the camera from the objects from the vertex position. So what we can do here is we need to find out what is the viewer position. So just for like showing what it is, we can write viewer position here. And if you think about this, we're in camera space. So what is the viewer's position in camera space? And after you thought about this, then it will be the origin. So the viewer is in the origin. And now we can calculate the vector from the vertex to the viewer. So this is what we want. And we want to normalize that. So it will be our vector v now, vector from the vertex to the camera. And we definitely want to normalize it. And so how to calculate a vector from one point to another, we will use subtraction. So viewer position minus the vertex position. If we do that, so if we are at the vertex position, so this is the position of our vertex, and we add the result of this subtraction to it, we will end up in the viewer position. So this will be the vector from the vertex position to the viewer position. And we normalize the result, and this will be our v. And then we need to find the direction towards the light source. So we need the L vector. This also needs to be normalized. And so this is pretty much the similar logic. We need to subtract vertex position from something, and that something will be light position. So if we add this result to the vertex position, like if you do something like vertex position plus this thing, then those will go away and you end up in the light position. So this is a vector from the vertex position to the light position. And this is normalized now, and we can use that in the formula as well. What we need to do is start calculating this color. There is still one more vector, so let's try to find that as well before we move on to the formula, the reflected light vector. And for this, we need to search this or find out about this reflect method. So if we Google that, we see that the reflect method will calculate the reflection direction for an incident vector. And it takes in the incident vector, and you need to specify also the normal vector, and in the result you will get the reflected vector. Now here is a formula that uses to calculate this, and I think somewhere in the materials there is kind of an explanation why this why this formula works. If you write it out and see what it geometrically does, then it's quite understandable how it operates. So we need an incident vector and we need the normal vector, because this will be the vector of the reflected light. We need to reflect, but now we need the incident vector, so the vector that is towards our vertex. So we need minus L here. So this is L, another one. So this is the same vector we had here, and we need the normal so that this is reflected correctly. Okay, one thing you might want to find is it mentioned here? No, it's not. Okay, so this probably is normalized, so it should be. Okay, it should be with the same size as this L is, or minus L. Okay, so now we should start calculating the color. Of course, like you can do this in another way. You can just find N and L and then find the diffuse shading or diffuse lighting term already here, and then add those other vectors as you need them. But currently we have defined all of our vectors. There are no errors in the code. And let's try to see if we can get this diffuse coefficient here, for example. So the diffuse coefficient is, well, we need the color of our object, and we said that let this color be for the material, let it be the same for ambient and diffuse, and we're not going to mess around with the light either. So let's say we have a white light, so we actually don't put any value, like this will be 1, and for this ambient light we'll need some small value, 0.05 maybe. We'll see what different values look the best there. But let's start with the ambient term first, the diffuse term first. So it's color times the dot product between the normal and the vector towards the light, right? So you can also see this from the material, and well, and from here, so you will need to use the dot product between the L and N for the diffuse term and V and R for the specular term. So this will be the diffuse term currently, and this dot product can also be negative here. So what we would need is we would need to take the maximum of 0 and that. This is one way of doing it. You could also write this other function called clamp here, but well, this won't be bigger than 1, so this should be okay. Let's see what happened. And yeah, so we have some shading. So this will be the raw diffuse shading. We can see that when the light is moving in our scene, different parts of this spherical object become illuminated, and other parts darker. Okay, now of course this dark area is way too dark, so what we can do is we can like add some small value, and what we say 0.05 maybe to this result. Now this is already maybe bigger than 1, but currently seems okay, so it's a bit lighter now. You can also try like different values. You can try some vectors here and see what happens. Okay, so now we basically have the ambient term and we have the diffuse term. Of course, if you want, you could write the same thing as just like take the color and then we add color times the dot product. So this line would more resemble the actual formula, and you could have like I think you could have a vector here that will do element-wise multiplication, and then you will have some different shade here. Nope, it does not work. What do I have? I have a bracket missing over, too much brackets there. So yeah, so now we have this weird ambient light that's green, very green ambient light all over the place, and this will do element-wise multiplication. But so this is if you want to have like some tone, some color tone for your ambient light. But we can use just some like small value here, and we don't need vector 3 if all of the components are the same. So, but yeah, this one would be more compact, but you would need to understand like that you have the ambient term and the diffuse term separately. And lastly, we would need a specular term, So that would be, let's leave the color white, because usually like the specular reflection is the reflection of the light source directly from from some like glossy material or some coating on the material, so it doesn't, the material's color really doesn't contribute to this term as much, so it should be white. There is this example in the materials as well, where you can like see what happens if you have like the same colored specular, so you don't even like see the specular, but if you have the different specular color, then you can see the white dot here. Okay, but let's add the dot product. So what we need here, we need dot product between the reflected light and the viewer vectors, and we need to raise this to some power. So let's raise this to maybe we're going to raise it to the 10th power and see what happens. And we would also need to ensure that this dot product is positive, otherwise we don't want to do anything with it. You could also like make a branch there, so if it's negative, then don't even go to that computation. So okay, there is no power method. Let's see GLSL. So we do need to have yes, so we need to put 0.0 there. Okay, and now we have the specular term, and I can't really see the effect. Oh, and of course we would need to remove this other line there. So now it should be, yeah, you saw that there was this bright spot there. We can check it out. We had 10 here, right? So what happened with 10? Okay, then we have this very big bright spot. So it's pretty much everywhere here, like on those vertices. Now, why is this behaving like it is? This is correct behavior, but is it what you want in your graphics? Like visual quality, that's something you should decide. Now, if you implement the same algorithm with fong shading, you should see a much better result. You should see something like as shown in the task description, something like this. So the specular highlight would be really distinguishable. It will be on the walls and so on. But with corrode shading, you will only see it like on these vertices. Now, why is it so? This is something that is asked in the task as well. So describe in the task submission why corrode is missing a specular highlight on the back wall. So if you implement fong, you should see this specular highlight on the back wall, but with corrode shading, it's not there. So try to explain that as well. So that's pretty much the first part of this task, and I will leave the second part to you. And yeah, so don't forget to explain the differences of those different shading models in the task submission, and don't forget those vertices, those vectors that are explained here. So really see like where do you need to take the dot product, what cosine between which vectors do you need for which components of the lighting model. And thinking about in terms of those vectors, so you have a surface, a point there, and surface normal, vector towards the light source, vector towards the viewer, the reflected light vector, and so on, is really beneficial for doing all sorts of computer graphics, visual effects later on in the course or in later projects as well. So have fun!